Okay, so let's dive into some examples. So some of these are real data, some of these, a few of them, one or two of them are made up data, and some of them are sort of in between where I've been able to get sort of means and standard deviations and so on for real data, and then I've simulated data. So I'm not using anything I think that's terribly unrealistic. So the first one, I've picked on another regional city in Australia, Ballarat, and we'll say that we're interested in knowing, we know that there are households in Ballarat that use firewood for heating. Quite a lot of households in Australia still do. It's quite surprising actually, I forget now, but it might be 20% of the population, something like that, or 20% of the households. So I'm assuming here, I actually don't know if it's true, that Ballarat has some system for licensing wood-fired heaters. They know where they are. I think here in Canberra, I think the government knows that, but we'll assume they know that because that helps us get our sample. So we're interested, perhaps for some public policy purpose, we might want to be looking at regulating them in some way, or you know, in Canberra we have a scheme to help people transition from wood-fired heating to other sorts of heating. Or we might be a business that's interested in selling firewood or heaters or other types of heating, but what we want to get an idea of is how much firewood people are using. If we know how much firewood a household uses, we've got some idea of how much energy it needs each year to heat its house. So what we do is we're in the fortunate position of being able to get a complete list of everybody in Ballarat who has, every household that has a wood-fired heater. And so that's nice when you can get it. One of the things that makes research difficult is very often you can't get that sort of thing. It's very frustrating. You wish you could and you can't. But we'll assume that we've got it. So, and the population that we're interested in is the people who are currently, let's say, for the moment, that our population we're interested in is the households in Ballarat that currently use wood for heating. So we're not interested in projecting into the future or anything like that. So we take a sample of 100 households, and we can do that in many ways, but if you've got a list of everybody and you want to take a sample, the easiest way to do it is you just create a table where one column is the list of everybody, and the next column is, you can do this in Excel, you have a function that generates a random number. So you put a random number next to everybody, and then you sort the list on the random numbers. And then if you want a random sample of 100, you just pick the top 100 people in the list, and they are randomly selected. I might put up a video later of showing how you do that, but that's a very common, simple way of doing it. In practice, the whole business of getting a good sample is often much more complicated than that. Now, what we want to do with this sample of 100 households is we want to find out, we want to make what we call a point estimate. What we're doing is, if we're just estimating a single number, we want an average, a median in this case, of how many tons of firewood a household uses every year. All right, so we asked them, how much did you consume in the previous year? When you're doing these sorts of studies, you've usually got to give some sort of a time frame to the respondents. And in this particular case, the responses you'll get will vary in their accuracy. So quite a lot of people will probably have bought firewood from a firewood supplier, and they've been doing it for years, and they know that they need 2 tons a year. But, you know, in regional Australia, there are mechanisms where people can go out into the countryside and into the forests and take their own firewood lying on the ground, and those people probably don't have a very accurate idea of how much firewood they've used, so it'll be a guess. But we get the numbers. Now, what we want to end up with here is a 95% confidence interval for the median. Okay, we want to be able to estimate a median and say how confident we are about that estimate. So I'll show you the calculation here. Don't worry too much about the way this is actually done yet. So what we have to do first and I touched on this briefly at the end of the last lecture. I showed you how to do it. We want to calculate something called the standard error. So the standard error represents the imprecision that you get because you're measuring a sample, not the whole population. If we went and asked everybody in Ballarat how much, everybody who used firewood, how much firewood they used, we wouldn't need to calculate a confidence interval because we could just calculate the median and we would know it. We'd know exactly what the median was. That doesn't mean that there wouldn't be some error, okay? So there's other kinds of error. The error, standard error, is the error that comes about because you're just using a sample of 100 and not the whole, whatever it is, maybe 10,000 or 15,000 people in Ballarat who heat their homes with fire. So another source of error would just be the fact that people, some people will be guessing, for example. So you can expect other types of error, but standard error is just error that is due to the fact that we're not seeing the whole picture, we're only seeing a small part of the picture, but the small part of the picture is supposed to represent the big picture. I like to think of it as sort of a little thumbnail of a photo where the thumbnail's a little bit pixelated and blurry, okay? It's basically maps onto the big picture, but it's losing quite a bit of, some information. So we do this calculation. So the calculation, it's important to look at the calculation to understand how it works, and we'll do that in a moment. But it's the interquartile range, so the third quartile minus the first quartile of our sample of 100, divided by the square root of the size of the sample, so that's the square root of 100, which is 10, and also divided by 1.08. Now, someone always asks where 1.08 comes from, and my answer to that, as it is to a number of things in this course, is some complicated math. There is a paper that explains this, which I can refer you to, but just take it on trust. This is a number, a lot of work went into coming up with that number to try to get something that was a reasonably good, somewhat conservative estimate of the standard error of the median. For those of you that have done a statistics course, what we're doing here essentially is we're doing for the median what you would do with a one sample t-test for the mean. It's essentially analogous idea. All right, now, so once you've got the standard error for something, and you can not just do it for medians, you can do it for means, you can do it for almost any statistic. There are ways of doing it. Then you can calculate a confidence interval. And the usual situation is that the confidence interval is plus or minus 1.96 times the standard error. So we'll look at the calculation in a sec. I just want to say something about this magic number 1.96. So when you learn statistics, you will come across this quite a bit. This is called a critical value. It's a critical value that is associated with a 95% confidence interval, and nearly all of the time when people quote confidence intervals, they use 95% ones. You will get some situations where, in very critical situations, vaccine clinical trials are an example where they might report 99% confidence intervals or even 99.9% confidence intervals. But 95% is very standard. You'll see it all the time in academic research papers. You can easily calculate different confidence interval levels, we call them. If you want 99%, you use 2.58 instead of 1.96, for example. And if you really want, I can give you a table of others, but to keep things reasonably straightforward in this course, as much as possible, I'll stick to 95% confidence intervals. Now, the median of our sample is 2.0 tonnes. And so here's how we calculate the 95% confidence interval. We know what our standard error is now. We've calculated it's 0.056 tons. That's 56 kilograms. So the 95% confidence interval is the lower end of it is going to be 1.96 times the standard error, and the upper part of it is going to be 1.96 times the standard error. So we did a little calculation there, and we come out with, rounded it here, 1.9 to 2.1 tons. So what we can state as a result of this exercise, assuming we did the sampling in a proper way, is that we're 95% confident that the median household consumption of firewood in 2020 in Ballarat was between 1.9 and 2.1 tons. Okay, so that, depending on the kind of decisions you're making, that can be a very useful bit of information. It tells you what the median is, and it gives you an idea of how precise that estimate is. Okay, that's actually a fairly precise, in that kind of context, a fairly precise estimate. Now, in this statement of what we can say, I've said 95% confident. Depending on the context, quite often we will just say we're highly confident. Okay, as soon as you start putting in 95%, that sort of invites questions from the audience about where did that 95 come from and what does it mean and so on. And sometimes you don't want to get into those discussions unless you have to when you're presenting results. Now, let's drill into this formula a little bit, because there's a few things to note. One of the things that is a good thing to learn to do, and most of you probably learned to do this in high school, is examine the formulas for things, because sometimes they will help you understand a bit more about what's going on. So when we're estimating standard error, so standard error, a lot of standard error formulas have a general configuration which is quite similar to this one. Okay, so in the top of the formula you have you have something which is an indicator of the variance of the data, and in the bottom you have something which relates to the size of the sample, usually the square root of the sample. It's very common. So the IQR is a variance measure, it's like the standard deviation for the mean. It's a variance measure. So because it's on the top of the formula there, what that means is that the greater the IQR, the greater the variance, the larger the standard error. And that kind of makes intuitive sense. So if everybody in Ballarat was using pretty much the same amount of firewood, then the IQR would be very narrow, and the standard error would be small, and the confidence interval would be narrow. Whereas if there was huge variation, then the IQR would be wide, the standard error would be larger, and the confidence interval would be wider. So there's a relationship between variance in the informal sense and standard error. Now, so the second thing is about the sample size. So you've got on the bottom there in the denominator, you've got the square root of n. So what this means is the bigger your sample, the smaller your standard error if everything else is the same. But the problem is, because it's a square root there, you have to make your sample 4 times bigger to make your standard error half as big. And so that, and I've encountered the direct effects of this back when I used to work. I spent a good chunk of my younger life, among other things, running ministerial offices. And every time there were elections, people would get very excited about political polls about, in electorates about how many people thought or what proportion of people thought they were going to vote for one party or another party. And the politicians, they're very focused on electorates where the contest was very close, where maybe 49% preferred one party and 50% preferred another, or something like that. So they get very worried about those, because those are the ones they wanted to concentrate on in the election. And typically these polls were done with a sample of 1,000. Now the problem is with a sample of 1,000, that gives you a standard error, I think, of about 1.5%. And so if they're telling you, if the results come back and they say, oh yes, well, you know, your party is preferred by, you know, 49% of the people in the electorate, but that's the confidence interval is what would it be, 47.5 to 51.5 or something like that. That would be regarded as almost useless information, because it meant they could win or lose the election in that seat. So the politicians would always say, can't you make it more accurate? Can't you get a more precise estimate? And the problem was that often, to get the kind of estimate that the politicians would want, you would have to not just quadruple, but, you know, kind of keep multiplying by 4. You'd have to be you know, surveying 64,000 people in an electorate that had, in some cases that I can vaguely recall, you know, 80,000 voters or something like that. It was just impossible. So that's one sort of real situation where that square root of n thing became a real headache. But in any kind of situation, you just need to be aware that if the precision isn't good enough, you're probably going to have to, you know, quadruple your sample size to reduce the standard error and therefore the confidence interval to half the size. Now, the third point, this is really, really critical thing to understand, and it's kind of magic in a way. There is nothing in that formula about the population. Okay, the IQR is the IQR of the sample of 100. The N is the size of the sample, not the population. Okay, this formula knows nothing about the population. It could be, you know, Ballarat with a population of, I think it's about 45,000 or something, or Sydney with a population of 7 million, or you know, whatever. Formula doesn't care. It will give you a confidence interval for the median based on a sample. So that is kind of the magical part of statistical inference, is that sometimes with a relatively tiny sample, you can get a useful estimate of something. But, and this is the fourth thing, this only works if the sample is genuinely representative of the population as a whole. Okay, it has to be this kind of thumbnail that maps onto the characteristics of the population, and that is often not easy to achieve. And this week and next week, and probably later in the course as we look at other examples, we'll come up against this again and again, is this problem of how do we get a representative sample. The ideal way, what we call the gold standard, is to use a random sampling procedure. Okay, so in a random sampling procedure, what we do, just bear with me a second, I just need to adjust my zoom here a bit. Okay, I think that's good. Okay, so random selection. So what random selection, the technical meaning of it, as I understand it, in this case would be every possible subset of 100 households, of however many households there are in Ballarat with wood-fired stoves, would have to have an equal probability of being chosen. So on my sort of guesstimate, I'd say 16,000 households in Ballarat who have wood-fired heaters. The number of possible samples of 100 households is enormous, okay, considerably more than the number of atoms in the universe. It's about roughly 2 followed by 262 zeros. That's a very big number. So every one of those possible subsets should have an equal chance of being selected. In practice, we don't talk about subsets. What we do is we talk about ensuring that every household had an equal probability of being in the sample. For practical purposes, it works out as the same thing. So don't worry about. Sorry, just give me a second here. Make sure I'm doing this right. Okay, good. Okay. Don't worry about subsets. I'm not going to ask you about that. Okay. I'm just telling you. The reason I'm telling you that is that sometimes this is explained in a rather confusing way in textbooks and things. And I know when I first learned it, because I actually studied set theory once in my life, I had questions about what it all meant, and people normally tell you the second version about each person having an equal probability, but the mathematically correct version, as I understand it, is this one about subsets. But you have no need to know that for practical purposes. Okay, so you just need to have, for random sampling, you've got to have some mechanism where you can put your hand on your heart and say, everyone in the population that we're interested in had an equal chance of being selected in the sample. But as we shall see, that's often not possible. Sometimes it's not possible because the population doesn't exist yet, again, as we'll see. So we're going to move on to another example. I'll just give you an opportunity, if anyone has any questions, to ask them now or pop them on the chat. Otherwise we'll kick on and look at some more. Okay, so our next example, this uses the data from that question in test 2 about the house prices in Cooma. So that was real data, that had there were 85 price values that I had in that data set. That was every sale that I could find that that met that criterion of having, I think it was 2 to 4 bedrooms or something like that. Now, this is an example of where we need to think about what's the population, okay, and what the sample is. So we can safely assume that the data we had was for every family home sold in Cooma in 2020, 85 data points. There's a term that we use sometimes. We talk about the population of interest. Now, what that means is, it means the same thing as population, what I'm talking about. So the population, if we're just interested in the family homes that were sold in Cooma in 2020, if that's our population, we don't need to take a sample, because we've got the price for every member of the population. We just work out the median, which is 365,000, and we're done. Okay, we don't need to do any more than that. But very often in these situations, we're not quite interested in a population which corresponds to the data we've actually got. What we're interested in is some kind of theoretical population, something like all the family homes that were or could have been sold in Cooma. Okay, or we might be interested in all the homes that might be sold this year. But let's say we're interested in all the family homes that were sold or could have been sold in 2020, ignoring the fact that if too many extra ones have been sold, if there'd been 200 houses sold instead of 85, then that might have pushed the prices down. But the reason we can be interested in this kind of partly theoretical population is we might want to compare Cooma with Ballarat, for example. Okay, and so we might want to do this kind of study for both regional cities and compare them. Okay, so there's the 5-number summary for that data, and all we need to calculate is the standard error. Is we need Q3, Q1, and the size of the sample, which is of course 85. Okay, so that's N, and then we do the calculation. And feel free to check my calculations. I do check them, but I still make mistakes. But I'm hoping that's correct. Okay, so just use the same formula and we come out with a standard error of about $23,000, 23K. So now that we've got that, we can do our usual little confidence interval calculation. So we want to subtract 1.96 times the standard error of 23,000 from the median. That gives us the lower end of the confidence interval. And then we want to add 1.96 times the standard error to the median to get the upper level of the confidence interval. So we do the sums there and we come out with that little pair there, which we can summarize as 95% confident that a family home sold in Coomera in 2020 would have achieved a price between 320 and 410K. So I've rounded them. The language I've used here is sort of includes a kind of hypothetical. Okay, so it's sort of a claim about what the price might have been for a house that wasn't actually sold. Now, I'm going to point this out because there's quite a substantial proportion of our class who have already done a statistics course, or they've done statistics in high school, so they know about t-tests. So from time to time I'm going to just mention other kinds of statistical tests, not because I'm going to examine you on them or expect you to know about them, but I think it's useful for you to be able to sort of match up what we're doing in this course with some other techniques that you've used, and some of which are more commonly used. So you can do exactly the same thing we've done for medians. You can do it with arithmetic means using something called a one sample t-test, and it will give you a confidence interval for the mean, not the median. Now, the arithmetic mean of this data set was 400,335. Remember, the median was 360. I think it was 365,000. Yep. So the mean is quite a bit bigger than the median, and the reason for that is it's pulled upwards mainly by these big outliers here. So we've got big outliers there. And it's also a little bit skewed to the right. So there's the right whisker here goes out further than the left whisker. The median is a little bit towards the left side of the box. So what you've got there is some of these extra higher values are pulling the mean up. Okay, and this is a characteristic of means. We say that they are not resistant to outliers. Another term we sometimes use is they are less robust. Robust has several related meanings, but so means have this problem, standard deviations have this problem as well, and the formula that you use in the t-test has the standard deviation on the top and then the mean is used in the confidence interval calculation. So your standard error is going to come out different. So if we do the t-test, we come out with where are the results here? Okay, we can say we're 95% confident that a family home sold in Coomera in 2020 would have achieved a price between 363 and 438. And we can also do the t-test without the outliers, and that brings the results a bit closer to what we got with the median. I think a good practice if you're using the t-test, and there are, strictly speaking, if there are outliers, you probably shouldn't use it. But if you do use it with outliers, you should run it with the outliers in the data and without the outliers, and see if the outliers have a hugely distorting effect on it. Sometimes they don't, and we'll see an example of that a bit later. So all that stuff about t-test, that's just for people who are familiar with it and would like to kind of match up what we're talking about here in this course with what they've already learned. Okay, any questions before we push on? Good.